Okay, in this video, we're gonna apply the general multivariate normal distribution and their MLEs to the classifications. Specifically, let's talk about the quadratic discriminative analysis, QDA. Okay, and let's see what has changed now that we use the multivariate normal distribution in its full. Compared with the QDA and the LDA we learned in lecture 7. Okay, actually the basic idea is very similar. Recall that to apply the quadratic discriminant analysis, we need to choose C. Choosing C. The idea is we're choosing a label C that maximize posterior distribution. That with max. Let me write down this one. With max posterior distributions, the x given x. Okay, so based on the data, which label has the highest chance? This is, so the idea is this one, and the L, the star is equivalent to maximizing the quadratic discriminant function. Quadratic discriminant function. Okay, so which is the QCX, which is given by, remember, the posterior distribution here is proportional to the probability x given equal x given y equal to c. Multiply the prior probabilities, prior information in our population, how much proportions of the individuals in this class C. Okay, so in other words, and this quadratic form is just equals to the natural log of this term. And recall that in our discriminant analysis, we assume given each class C, this X follows a normal distribution. So in other words, we are taking the log fx given y equal to c x multiply the pi c. And this can be simplified as the constant part does not matter. So to maximize this part, you can ignore the constant part, and then taking the log can get rid of the exponential part, the Q function part, right? So this will equals to -½ x minus mu c transpose inverse x minus mu c minus 1/2 natural log determinant of the covariance matrix among the class C, and plus natural log of the pi c. Okay, So in other words, we just find each class, and for each class we estimate the mu c and the sigma c, and we just calculate this QC function, and then we pick the class with the highest QC value, quadratic function decision function value. So here in this example, we have two class problem. We have the class C and class D. And in the original data set, we have the two class. And then we fit the normal distributions, two multivariate normal distributions. So for all the data points labeled with C, we fit one multivariate normal distribution. And for all the data points classified as D, we fit another normal distribution. And then based on the parameter we estimate from the maximum likelihood estimation, we check the QC function values. Okay, and the data point with the higher QC value, Q function values, we choose that as a prediction function. Okay, so in other words, say for two class problem, because each of the Q function is, so remember the decision function is given by decision function is given by QCX minus QDX, which is quadratic. Is a quadratic. Okay. So this implies the decision functions will be quadratic. Decision boundary is quadratic. Okay. For example, so here we have the two fitted normal distributions here, and we can also calculate the QC minus QD decision functions. We set those equal to 0, so within this zero plane, okay, so that's gives us a decision function, so which is given by so this is a decision function. Okay, probably if the data points falls into this region, we predict as class C. If a point falls into this region, we predict the class D, which makes sense, right? Because for each given point, we can see if this decision function is greater than 0, this tells us the likelihood of this point is higher for the class C than the class D, and vice versa. So this is the intuitions of the QDA problems with a general normal distribution assumption setting. And we talk about last class that one advantage of the QDA is the posterior distribution tells us not only the classification where this data points belongs to, but also give us the posterior probabilities. So the posterior probability probably P y equal to C given X equal to C. Okay, so now suppose you have a data point. Oh, you think, oh, this classification QDA predicts this label should be class C. Okay, but now we can further give you a solution not only with the label but also give you the probability. So, for example, there is a patient with this classifier diagnosed with cancer, but not only we label this new patient as a cancer patient, but we can also answer the question, oh, you labeled as a cancer, but has a 60% chance to have the cancer. Okay, so it can be answered giving the probability, not only give the label but also give the probability the individuals falls into that label, fall into that class. This probability can be calculated by using QCX, QDX. And this S is logistic function. For example, this is just 1/1 minus e to the power negative x. And we can also actually identify the decision boundaries from this posterior probability. If the posterior probability equals to 50.5, okay, so this means we are 50%. So a data point fall into this line means there is a 50% chance it falls into the class C or fall into class D. Okay, so that's how we apply the multivariate normal distribution for the QDA. Actually, the above methods also works for the multi-class. Also, the above QDA also works for multi-class case. Okay, for example, in our first class, we introduced a MNIST data set, which asks you to label classify the digits, right? And in that case, you just pick the one with the greatest. So that's the case. You just fit 10 different multivariate normal distributions, and then you pick. So step is similar. You fit multiple normal distribution. Step 2. Pick the class. With greatest quadratic discriminant. With greatest quadratic discriminant.